Welcome to the Explainer. Today, we're diving into a massive paradigm shift happening right now in the world of computing. You see, artificial intelligence is getting a major upgrade. It's moving away from just spitting out static forecasts about the future to actually anticipating human strategy and behavior.
Okay, to get started, let's look at this fascinating paradox. Think about it. In the real world, a perfectly accurate prediction can instantly become false if people act on it, right? Imagine an incredibly smart algorithm tells everyone that a specific stock is going to shoot up 10% tomorrow. Well, what happens? Everyone rushes to buy it today. That massive human reaction fundamentally alters the market, which means the original timeline and the outcome of that prediction are just completely thrown out the window.
Which leads us directly to the central question of this explainer. What happens when the world reacts to the algorithm? This question exposes the ultimate blind spot in modern forecasting. Historically, algorithms have kind of just assumed the world will sit perfectly still and let itself be predicted. But we know humans aren't like that, right? We're strategic, we adapt, and yeah, we totally game the system.
All right, let's jump into section 1, when predictions fall short, also known as the static data problem.
Let's lay down a quick definition. Traditional predictive AI uses machine learning models to analyze historical data and forecast future outcomes. Honestly, you can think of it like a high-tech farming almanac. It looks at decades of past weather patterns to tell a farmer the absolute best day to plant their seeds. And, it's incredibly powerful for static environments where the past is actually a reliable map of the future.
Just to clarify our terms here for a second, we are strictly talking about predictive AI today, not generative AI. So while generative AI focuses on creating entirely new data, like, say, writing a poem or generating a cool image, predictive AI is all about categorizing or forecasting existing data points to tell us what's most likely to happen next.
So the absolutely crucial point is this. What happens when a prediction actually changes how people behave? Traditional predictive AI has a glaring flaw here. It wrongly assumes its environment is totally static. It acts like it's predicting the weather, and hey, the weather doesn't care that you predicted it. But when you start predicting human behavior, well, humans change their behavior based on your forecast. Moving on to Section 2, the game theory upgrade for dynamic environments. This is where we find our missing puzzle piece, game theory. It's basically the mathematical framework for analyzing strategic interactions among rational agents, or even those with limited info, what we call bounded rational agents. By integrating this math, we essentially shift the AI's job from simply predicting the weather to playing a highly reactive game of chess. The AI now actually knows that its moves are going to provoke a countermove. If we compare the two, traditional AI relies heavily on static data and simple pattern recognition. But game-theoretic AI, it totally expects dynamic environments. In fields like algorithmic game theory, the AI is literally designed to expect strategic manipulation from users. It anticipates that independent agents might, misreport information to manipulate outcomes in their favor, and then it goes ahead and adjusts accordingly. And this leads to some pretty wild behavioral quirks. When researchers evaluate modern large language models using classic game theory scenarios, like the famous prisoner's dilemma, they find some really surprising traits. For instance, these models often show a pro-social bias. They'll actually prioritize fairness and mutual cooperation over ruthless mathematical optimization. They're effectively learning how to model their opponents and calculate risk, approximating what economists call a Nash equilibrium, which is just a stable state where no one really benefits from changing their strategy. Let's take this foundational theory and look at some real-world arenas. Section 3, outsmarting the stock market with hybrid forecasting. This whole concept is brilliantly illustrated in some recent academic research. A fascinating study from the Journal of Informatics Education and Research shows that traditional analysis methods completely fail to capture the sheer immense complexity of modern market volatility. Standard algorithms just end up getting lost in the noise of sudden market shifts and unexpected events. To fix this, researchers have developed what they call a hybrid forecasting model. Here's how it works. Step 1. Machine learning still does what it does best, processing absolutely vast historical datasets to find complex patterns. But Step 2 is where the magic really happens. Game theory steps in to model the strategic interactions. Because as we've learned, finding a pattern just isn't enough. The AI has to anticipate how other human traders will strategically react to that exact same pattern. Finally, in Step 3, the predictions are refined based on those equilibrium conditions we talked about. So why does this matter to us? Well, if you're an investor, pure quantitative machine learning is honestly kind of a blunt instrument. By integrating behavioral game theory, you start capturing emotional biases and herd behavior. You account for the messy reality that human investors aren't perfectly rational. You combine that with Nash equilibrium analysis to figure out where the market is likely to stabilize, giving you a massive, multidimensional edge. Now let's pivot to another high-stakes arena. Section 4, the cybersecurity chess match against active adversaries. In cybersecurity, there's this intense multi-stage battle between an attacker's cyber kill chain and a defender's reactive cyber defense chain. The problem is, traditional defense is purely reactive. It just sits there, waits for an anomaly, and then tries to block it. But smart attackers, they don't just trigger alarms. They slowly alter their behavior to blend right into the background noise, basically rendering those static defenses completely useless. To actually win, defenders have shifted to game-theoretic cyber defense, and honestly, it's incredibly clever. They use mathematical models called Stackelberg games to anticipate the attacker's absolute best response. They deploy active cyber deception, like honeypots, to trick the attackers into revealing themselves. They even use randomizing monitoring intensity just to keep the adversary guessing. It's an active, highly strategic defense that figures out the attacker's next move before they even make it. All right, let's zoom out to the big picture paradigm shift here. Section 5, Strategic Coevolution and Shaping Human Behavior. Recent research on evolutionary prediction games perfectly captures this profound new reality. The paper states, and I quote, "When predictive computing algorithms serve populations of users, they do not merely observe behavior, they actively shape it." Think about that for a second. We aren't just looking at passive data anymore. We are caught in a fully dynamic feedback loop. Think about how this plays out on the platforms you use every single day. In these evolutionary prediction games, prediction accuracy actually acts as a scarce resource. If a group of users gets really great predictions, they engage more, they invite their friends, they generate more data, and that makes the algorithm even better specifically for them. This creates literal natural selection dynamics, a kind of mutualistic symbiosis between the algorithm and the specific user groups it serves best. Which leaves us with one final, incredibly provocative thought to ponder today. In a world of strategic coevolution, where the AI anticipates our moves and we constantly adapt our strategies based on the AI's outputs, are we predicting the algorithm's behavior, or is it actually predicting ours? Thank you so much for joining me for this explainer. Until next time, keep questioning the patterns around you.